So we'll take our first look at diffraction by shining this monochromatic laser through a diffraction grating. And we'll shine the results onto this poster board over here. This diffraction grating diffracts the light off into beams on either side. This is a little material with many slits, so that light that hits it anywhere diffracts. So we can see a bright spot in the middle, and on either side, the points where the red light is diffracted to. Now let's see what happens if we use a different wavelength of light. Green has a shorter wavelength, and we can see it diffracts at a smaller angle. The bright spots are closer together. And we can see this even more pronounced when we look at an even higher frequency light. So if you have light that has multiple wavelengths in it, you can use a diffraction grating to separate them out. Now if we start turning our diffraction grating to the side, we can see that there are actually multiple peaks. Spaced out regularly. Incandescent lights, like this overhead projector here, create a spectrum of frequencies. What we detect as white light is the combination of red, green, and blue. So we can see that entire spectrum if we send it through a diffraction grating. I'll start by narrowing down the light, this will make it easier to see the diffraction, and then I'll send it through the diffraction grating. And we can see our complete spectrum from indigo to red. If you shoot light at a narrow opening, it's going to diffract, which is to say, at the corners, it's just going to shoot every which way. If we start with all the light waves in phase with each other, like if we had a coherent laser beam, then the light coming off of here and the light coming off of here will form a nice interference pattern when we shine them on this wall over here. So if we look at the point straight across from the middle, where light from this corner travels the exact same distance as light from this corner, they'll stay in phase at the end, and we'll get a nice big bright spot. But if we pick a spot further down, where light from this corner has to travel, say, exactly half a wavelength further than light from this corner, maybe we'll get a dark spot. And then as they shift back into phase, we'll get another bright spot down here. The corresponding pattern of bright and dark patches is going to look something like this. You know, bright patch, bright, dark, dark, bright, forming something of a sinc function. If the slit is extra large, you won't notice much diffraction. But as the slit grows smaller and smaller, the pattern becomes more apparent. Now, of course, we can double the fun if we double the slits in Young's double-slit experiment. If we shine the light on two slits and zoom out further, we can show both slits shooting out omnidirectional light that forms its own interference pattern. So now light from this whole slit interferes with light from this whole slit. So if we look at the point in the middle of them, we once again get a bright spot. If we look at a point where one of them has to travel exactly half a wavelength further, we get a dark spot, light, dark, light, dark. So we once again get a series of patches of light, dark, light, dark. But we can't forget that each individual single slit is creating an interference pattern. So we have to modify the pattern of interference from two separate slits with the pattern that emerges from each single slit. So we get a patch of patches that gets darker and then brighter again. And here we will shine a laser through 4 different pairs of slits of varying size and separation.